Come with me on a journey, not across oceans or continents, but through time and space itself, guided by the brightest beacons of human intellect. We're about to embark on a grand tour of the cosmos, exploring the landmark Nobel Prize-winning discoveries that have fundamentally rewritten our understanding of the universe. Since 1905, these moments of profound insight have acted as cosmic signposts, pointing us toward a deeper, more intimate connection with the fabric of reality. Each discovery is a story, a testament to our relentless curiosity and our unyielding quest to find our place among the stars. This isn't just a history lesson, it's a celebration of the human spirit's ability to grasp the unimaginable. From the smallest packets of light to the cataclysmic collisions of black holes, these breakthroughs are the pillars upon which modern astrophysics and cosmology stand. They have peeled back the layers of the cosmos, revealing a universe far stranger, more dynamic, and more magnificent than our ancestors could have ever dreamed. These are the ideas that have shaped not just our scientific models, but our very perception of existence. So buckle up your imagination. We're going to travel back to the dawn of quantum mechanics, listen to the echo of the Big Bang, witness the birth of exotic stars, and feel the very ripples in space-time. Together, we'll trace the intellectual lineage of discovery, appreciating how each Nobel-winning insight built upon the last, constructing the awe-inspiring cosmic perspective we hold today. This is the story of how we learned where we are, what we are, and how the universe came to be. Our journey begins not in the depths of space, but with a puzzle of light. In 1905, a young Albert Einstein, a name we'll meet again, turned his attention to a curious phenomenon, the photoelectric effect. Scientists knew that when you shine light on a piece of metal, it can knock electrons loose. But the details were baffling. A dim blue light could free electrons when a bright red light could not. The energy of the electrons didn't depend on the light's brightness, only its color. It was a paradox that classical physics, the laws of Newton, couldn't explain. It was as if the universe was whispering a secret, waiting for someone to listen closely. Einstein listened. He proposed a revolutionary idea. What if light isn't just a continuous wave, but also a stream of tiny, discrete energy packets? He called them quanta, which we now know as photons. Each photon carried a specific amount of energy determined by its color or frequency. A blue photon simply has more of a punch than a red one. It wasn't about the number of photons hitting the metal, but whether each individual photon had enough energy to do the job. This elegant solution, which earned him the 1921 Nobel Prize in Physics, was more than just an explanation. It was the key that unlocked a new reality. This discovery became a cornerstone of quantum mechanics, the strange and wonderful set of rules that govern the universe on the smallest scales. Without it, we couldn't understand how stars shine, how atoms hold together, or how to build the very sensors in our cameras and telescopes that allow us to capture images of distant galaxies. It's the fundamental language of light and matter. Einstein's insight into a seemingly small laboratory effect gave us the tools to decode the messages sent to us across billions of light years, from the heart of the sun to the most ancient starlight in the cosmos. Now, let's fast forward. Imagine tuning an old television set to a channel with no station. That static, that snow you see and hear, a tiny fraction of it is cosmic in origin. In the 1960s, two American radio astronomers, Arno and Robert Wilson, were working with a large horn antenna, trying to eliminate a persistent, faint, and annoying hiss that came from every direction in the sky, day and night, no matter where they pointed their instrument. They checked everything. They even cleaned out pigeon droppings, thinking it might be the source of the interference. But the noise remained, a constant low-energy hum from the universe itself. What they had stumbled upon, completely by accident, was monumental. At nearby Princeton University, a team of physicists led by Robert Dicker had predicted that if the universe began with a hot, dense explosion, the Big Bang, then the leftover heat, the afterglow of that creation event, should still be detectable today. It would have cooled and stretched by the expansion of the universe into a faint bath of microwave radiation, filling all of space. Penzias and Wilson had found the very echo of the Big Bang. Their discovery, recognized with the 1978 Nobel Prize, transformed the Big Bang from a compelling theory into an observational fact. This cosmic microwave background radiation, or CMB, is the oldest light in the universe, a fossil from a time when the entire cosmos was a hot, opaque fog, just 380,000 years after its birth. It's a baby picture of the universe. By studying the minuscule temperature variations in this ancient light, we can learn about the universe's age, its composition, and the seeds from which vast cosmic structures like galaxies and galaxy clusters would eventually grow. That persistent hiss in a radio antenna became one of the most profound signals we have ever received, connecting us directly to the dawn of time. The life of a star is a dramatic tale of a battle between gravity and pressure. For most stars, like our Sun, this is a long, stable story. But what happens when a truly massive star dies? Its core collapses under its own immense gravity, crushing protons and electrons together to form a city-sized ball made of neutrons, an object so dense that a single teaspoonful would weigh billions of tons on Earth. This is a neutron star, the celestial corpse of a giant. For a time, these were purely theoretical objects, the stuff of mathematical fancy. How could we ever hope to find one? The answer came once again as a surprise. In 1967, a graduate student named Jocelyn Bell Burnell, working with her supervisor Anthony Hewish, detected a strange signal using a radio telescope. It was a pulse, a bit of scruff, that repeated with astonishing regularity, once every 1.33 seconds. At first, they half-jokingly labeled it LGM1, for little green men, because no known natural phenomenon could produce such a precise metronome. Soon, they found more of these pulsating signals from other parts of the sky, and the truth became clear. They weren't detecting alien civilizations, but something just as extraordinary. They had discovered pulsars. These are rapidly spinning neutron stars with powerful magnetic fields that sweep beams of radiation across the cosmos like a celestial lighthouse. Every time that beam sweeps past Earth, our radio telescopes register a pulse. This discovery, which led to the 1974 Nobel Prize for Hewish, gave us our first confirmation that neutron stars were real. Pulsars are incredible cosmic clocks, and by studying the tiny variations in their timing, we can test the laws of gravity in extreme environments, search for gravitational waves, and deepen our understanding of the final, violent stages of stellar evolution. The scruff in the data was the heartbeat of a dead star. For most of the 20th century, cosmologists wrestled with one of the biggest questions. What is the ultimate fate of the universe? We knew since Edwin Hubble that the universe was expanding, but gravity, the attractive force of all the matter within it, should be acting as a brake. The expansion should be slowing down. The great debate was whether it would slow down enough to eventually reverse in a big crunch, or if it would expand forever, slowing but never stopping. Two independent teams of astronomers set out in the 1990s to settle the question once and for all. They used a specific type of stellar explosion, a type Ia supernova, as a standard candle. These supernovas have a known, consistent brightness, so by observing how faint they appear from Earth, we can calculate their distance with great precision. The teams painstakingly hunted for these distant explosions to measure the expansion rate of the universe deep in the past. They expected to find evidence of a slowdown. Instead, they found the exact opposite. The distant supernovas were fainter than they should have been, meaning they were farther away than expected. The expansion of the universe wasn't slowing down, it was speeding up. This was a bombshell. It was like throwing a ball into the air and watching it accelerate upwards into the sky. The discovery, awarded the 2011 Nobel Prize, was shocking and profound. To explain this cosmic acceleration, physicists had to invoke a new mysterious entity that makes up nearly 70% of the universe. We call it dark energy. We don't know what it is, but it appears to be a property of space itself, a kind of anti-gravity that is pushing the cosmos apart at an ever-increasing rate. This discovery completely changed our picture of the universe's past, present, and its ultimate lonely future. Let's return to Einstein. His general theory of relativity, published in 1915, described gravity not as a force, but as a curvature of space and time caused by mass and energy. Think of a bowling ball on a trampoline. It creates a dimple that causes smaller marbles to roll towards it. Einstein's theory also made a startling prediction. When massive objects accelerate through space-time, they should create ripples in its very fabric, like a boat moving through water. These ripples, called gravitational waves, would travel outwards at the speed of light, carrying information about their violent origins. For a century, these waves were the holy grail of physics. They were predicted, but their effects were so fantastically tiny, stretching and squeezing space-time by less than the width of an atomic nucleus over a distance of several kilometers, that detecting them seemed impossible. But we built an instrument of exquisite sensitivity to listen for this cosmic symphony. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of two enormous L-shaped detectors, thousands of kilometers apart, that use lasers to measure infinitesimal changes in distance. On September 14, 2015, it happened. A clear, unambiguous signal arrived at both detectors. It was the chirp of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging in a cataclysmic event 1.3 billion years ago. The gravitational waves from that collision had traveled across the universe to finally wash over the Earth. This first ever direct detection, which earned the 2017 Nobel Prize, was a triumph. It not only confirmed a major prediction of Einstein's theory, but also opened a completely new window on the universe. We can now hear the cosmos, listening to events that are invisible to our telescopes, like the collision of black holes and neutron stars. Our journey through a century of discovery reveals a profound truth. The universe is not static, and neither is our understanding of it. We've traveled from the quantum nature of light, which allows us to even see the stars, to the very echo of creation itself, the cosmic microwave background. We've visited the bizarre stellar corpses known as pulsars, confronted the shocking reality of a runaway universe driven by a mysterious dark energy, and finally, we've learned to hear the symphony of space-time through gravitational waves. Each of these Nobel-winning insights was a revolution, a paradigm shift that opened up entirely new cosmoses to explore. These discoveries are more than just facts in a textbook. They are milestones in the human adventure. They represent our collective ability to ask audacious questions and build incredible instruments to answer them. They connect us to the universe in the most intimate way possible, showing us that the same physical laws that govern a laboratory experiment also choreograph the dance of galaxies. Our cosmic address book has grown from a single planet to a universe of unimaginable scale, strangeness, and beauty, all because of this relentless spirit of inquiry. The journey, of course, is far from over. The edge of knowledge is always expanding, and with it, the shore of our ignorance. Dark energy and dark matter remain profound mysteries. What lies inside a black hole? Are there other universes? The next great discovery is out there, waiting. But now I want to hear from you. Of all these incredible breakthroughs, which one resonates with you the most? Is it the quantum spark, the echo of the Big Bang, or the ripples in space-time? Let me know in the comments below. Keep looking up.